Hello everyone and welcome to the Euclid video tutorial series. I'm Shubhana Hemmati, scientist at Caltech IPAC and ENSCI, the Euclid NASA Science Center at IPAC. This series is produced by ENSCI together with IRSA, the NASA IPAC Infrared Science Archive, to help you get started with Euclid's first public data release. I'll be your host for this first video and a few others in this series. What this series covers are 7 videos across data products, access tools, and worked science cases. The first one, which is this current video, is an overview of the Euclid mission and its data products. If you're already very familiar with Euclid, then skip to the rest. Video number 2 is Euclid Data Explorer. It's IRSA's interactive web GUI, which it offers for all of the missions it hosts. It lets you look for your objects of interest, search among different catalogs, visualize different things, make simple plots without having to download big chunks of data. Video number 3 is Python Firefly. It's another visualization tool that lets you play with different images and spectra, but this time it sits right next to your code, so in your Python or Jupyter notebook. Video number 4 introduces the NASA Fornax compute platform, where your code sits next right to your data, and you don't have to use your own laptop or machine to do computation, and you can use this platform. Video number 5 talks about how to access the Euclid data on the cloud, specifically on Amazon Web Services S3 buckets. This is in 2 different sections, and it shows you how to access Q1 data, images, and catalogs. The future data releases will also be very similar. Then last but not least, there are 2 science examples, one on galaxy clusters and one on AGNs, and both of which just showcase how Euclid Q1 data can be used to answer science questions. Now, getting to what Euclid is an ESA M-class mission to study the geometry and nature of the dark universe. It was launched back in July 2023, a 6-year mission at L2. It's a 1.2 meter telescope operating at the optical and near infrared from 0.5 to 2 microns. It will survey 1/3 of the sky, about 14,000 square degrees, and it's run by a consortium of more than 2,600 people across Europe, US, Canada, and Japan. Contribution from NASA to Euclid are the 16 near IR detectors, as well as 3 nominated US science teams to do science with the Euclid data. NASA has also established ENSCI, our team, at Caltech IPAC in Pasadena to support US-based investigations using Euclid data. ENSCI is also one of the 11 data processing nodes of Euclid. Euclid has 2 main archives, one at ESA and the other one here at NASA IPAC IRSA. At ENSCI, we also provide algorithms and software development for calibration of the NISP data, and we also offer a help center. So if there are any questions with Euclid data, you can go to our website, euclid.caltech.edu, and ask your questions, submit a ticket that comes to us. We also provide documentations and tutorials about Euclid. Now, why Euclid? Because everything that we see, all the stars, all the intergalactic gas, dust, etc., all the ordinary matter, it's only 4% of the energy budget of the universe. The rest, dark energy and dark matter, that we don't know too much about. So that's the main idea of why we need cosmology missions. Now, the 2 main science drivers of Euclid are weak gravitational lensing and galaxy clustering. Weak gravitational lensing sits on the idea that matter bends light, so dark matter that sits between us and background galaxies distorts the shapes of the galaxies. Even if these distortions are super small, if we study them statistically, we can learn about the intervening matter. And the idea of galaxy clustering is that the sound waves that propagate from the early universe, they imprint a standard ruler, what we call a baryon acoustic oscillation, and we can measure that from the way the galaxies cluster. Now, how does Euclid get to these science cases? With 2 instruments. One is WIS, which is its optical imager. It has a wideband imaging that covers from 550 to 900 nanometers. It will reach the depth of 24.5 magnitudes at 10 sigma. With with this wideband imaging, which has a very good resolution, so a pixel scale of 0.1 arcsecond per pixel, we can measure the shapes of about 1.5 billion galaxies, which is very useful for measuring weak lensing. Here, the field of view of WIS is shown compared to the full moon, and here you see the WIS instrument during integration. The other instrument is NISP, which offers both imaging and GRISM spectroscopy. Imaging is in 3 bands, Y, J, and H band, that will reach the depth of 24 magnitude at 5 sigma. And there are 2 GRISMs, one red and one blue, which covers 1.2 to 1.8 micron and then 0.9 to 1.3 micron. The spectral resolution of the GRISM would be about 400 and the spatial resolution of 0.3 arcsecond per pixel. NISP enables photometric redshift with the 3 bands, as well as GRISM spectroscopy for about 30 million galaxies, mostly at this redshift where we have prominent H-alpha emission from galaxies. You see example of the 16 NISP detectors and a zoomed in section here, and you see an example of the GRISM image here, and the NISP instrument during integration here on top. This diagram here, taken from a Q1 released paper by Hervé Assel et al., shows how the data is processed in Euclid, and the idea of showing it here is to familiarize you with different names such as Viz, Near, Mer, Seer, etc. that you will hear in the future videos. So to simplify this a bit, when the data comes from the telescope, it's in the raw format or level 1. When it's processed, it's level 2. And then when it goes to science, it will be level 3 for Euclid. The data that comes is in Viz and NISP, and there are some housekeeping data. So here are the calibration products, here are the data. There are some data that are external data, come from other telescopes, but are needed to do some things, for example, measuring photo Z, etc. All of these, after being processed, are merged into both same scale images and catalogs. So MER is the team that does that and provides the MER catalog and MER images. SEER is the spectroscopic data of Euclid that uses the MER detections to process the spectra, to extract them, etc. The spectra then goes to SPE, which measures the spectral lines from the spectra that SEER provides, and then that's where you get the SPE catalogs. PHZ is the Photo Z team that uses the MER catalog to measure Photo Z and provides the Photo Z catalogs, etc. So in future videos, when you are trying to search for data, you would know what keyword to use if you're looking for MER mosaics, for example, which are just Viz or Near images brought to the same pixel scale, or if you're interested in line measurements, you would look for SPE catalogs, etc. So this can be your go-to figure if you want to search for some kind of data, for example. Also, it's good to mention that all of these teams, so there is an organizational unit, OUVs, OU-NEAR, OU-X, OU-MER, etc. They have published their own Q1 papers, so you can just search for example, OUVs Q1 and get all the details about each of these processings separately. Now talking a bit about the Euclid survey. So as I said, Euclid will cover about 1/3 of the sky, 14,000 square degree in the wide survey, but it will also do 3 deep fields, which will cover about 53 square degrees. Those 3 fields are the Euclid Deep Field North, Euclid Deep Field South, and Euclid Deep Field Fornax, that it will visit more often to get deeper compared to the wide survey. There are also monthly 4 degrees squared self-calibration field that will be deeper than wide. Here is a timeline figure to show when the launch was, when the Q1 data got released, and DR1, which will be in fall 2026, and what will happen in the future releases. Q1 release, which is currently public and which all these videos are based on, you'll have the deep fields, but in the wide depth, because they are not visited as often as you'll have when the mission is complete. And the products are VIS and NISP imaging, NISP spectroscopy, and the catalogs and masks. As I said, there are two archives. One is here at NASA IPAC IRSA, and the other one at ESA. And DR1, which will be released, it will be 1900 square degrees, and it will reach about 24 to 24.5 magnitude in the wide. Okay, that's about it. I just want to also show some useful links here. If people are interested, you can read all about ESA Q1 data release here at the ESA website. You can read the data product description, which defines every basically column in the catalogs that are released, and you can learn all the detail from this DPDD, data product description. There are the Euclid tutorial notebooks here on this address, and the IRSA Euclid webpage, which explains more about Euclid and data access here, and our ENSCI webpage is at euclid.caltech.edu. Hope this was useful.